Cl minus would be our oxidizing agent?
Yes. They went out with water.
Okay.
Which means that water will be the reducing agent on the right side.
Reducing agent on the right side?
I think
That's it.
Should we be writing this in our plan?
Yeah, you write this just on the notebook. Anybody else? I mean, do you guys, your consensus here? So we have ClO3 minus, Cl minus, and then H3O plus is the oxidizing agent.
And then chlorine gas, that would be the oxidizing agent. And then water is reducing.
Okay, so we have this one, which is called option A, option B. Similar, but different. Are there any other? Are there any other options here? Or does this pretty much sum it up? No other? Or just don't know how to do this? Maybe? Well, which one would you go with then? Is it just a random guess as to which one you'd go with? Or do you have some method that you have? What's your... Yeah, okay.
Since this is a redox reaction,
Yeah.
if we're having a, what is it? I forget the word. Intermission. If we're having a transfer of protons, right, or the moving of electrons, then whatever is losing electrons or gaining electrons will be a reducer or oxidizer.
Okay.
So my theory for why I chose is that Cl should have a formal charge of, should have a oxidizing charge of -1, right? If it's just by itself.
This one here?
Yes.
Okay.
It should be -1. But the Cl on the other side would be +5 to match the O, right? Which means that I would have more.
Okay, so this Cl you're saying has an oxidizing charge. Oxidation state is actually the charge, the apparent charge, if we assume the 100% ionic bonding.
Yeah.
Here, there's no bonding. This is going to be the actual charge. So this is the charge on the chlorine.
So the actual charge would be -4.
Yeah, and so this is the oxidation state, and it's also the formal charge too. It's the same. So that's good.
On the other one, for ClO3, the formal charge would not full. The oxidation charge would be 5.
On which atom?
ClO3 minus.
On which atom? Or the whole thing? Or when you say +5, where does the +5 go?
Chlorine.
On just chlorine?
Yes, would be +5.
Okay, so just on chlorine we have +5.
Right.
Okay.
And then on the right side, water would have its usual oxidation charge, -2 for oxygen and +1 for hydrogen.
Okay, -2 for oxygen, +1 for hydrogen. Yeah, that's the
And then
usual.
for Cl2,
Uh-huh.
it should be 0.
Cl2 should be 0, that's correct. 2 times 0 will give me 0.
Which means that if we're going from electron movement, we're going from -1 to 0 using, was it chlorine as an oxidizer to receive a proton.
Okay, so we're going from -1 to 0. That means, when you say chlorine, you're talking about this or are you talking about this? Because this one I don't call chlorine, I call chloride, yeah. So are you talking about chloride as the oxidizer?
Yeah.
Okay, so chloride's the oxidizer because it's going from -1 to 0. And in going from -1 to 0, what did it do?
It gained
It gained 1 electron.
They gained 1 proton.
It gained 1 proton. If it gained 1 proton, then that means chlorine normally has 17 protons, so that means it has now 18 protons. And it gains 18. It has 18 protons, and it changed its proton.
It would lose an electron. Sorry.
It would lose an electron. Yeah, redox. We don't mess with the protons. The people who mess with protons are not the regular chemists. They're not the theoretical chemists, although theoretical chemists might. Yeah, it's the nuclear theoretical chemists. On the experimental nuclear chemists, they mess with the protons because they want to make new isotopes. But we don't want to make any new isotopes. We just want to use existing isotopes. What's naturally found in nature.
We'd be losing an electron.
We'd be losing an electron. So -1 electron per chlorine. And then we have how many chlorine? We have 5. Actually, we have 5 chlorides. So that would actually be a 5 times. So altogether, we're going to lose 5 electrons, right? But each chloride loses 1 electron. Okay. So where do those 5 electrons go?
They attach themselves to hydronium to form water.
Okay, they attach themselves to hydronium to form water. So where in hydronium do they attach themselves? To the hydrogen or the oxygen in water, or just the whole
They
thing?
would attach themselves to the oxygen.
To the oxygen?
Because the hydrogen wouldn't be able to fit them. It would only do one bond.
And then oxygen can fit them. And where in oxygen do they fit? Well, they just, so if we add 5 electrons to hydronium, that's 6 hydroniums. So what will form is H3O. So if we take an H3O plus and add an electron, then do we form H3O? Trihydrogen monoxide? Is that how it works? Oh. Well, if we look, remember I drew the Lewis structure for hydronium yesterday? Where do the 5 electrons go? Or where does 1 electron go? We got 6 hydroniums, so we're going to accommodate it. Where should I put that electron? Should I put the electron here on oxygen? Absolutely, yes. Yeah, that's right. That would take it from plus. It was originally plus. But if I add the electron here to the oxygen, I can get rid of the positive formal charge. And then it works out perfectly because then I have 1, 2, 3, 4, 5, 6. When we're counting formal charge, and oxygen is supposed to have 6 valence electrons. But you're violating a rule that should never, ever be violated. The octet rule. The octet rule is never, in fact, in Chem 4, I say it's not really a rule for the second period, it's a law. It's an octet law. Rule, you think, we can violate rules. It's no big deal. We'll just violate. You can violate the rules for third period, the third row, and below, because we have things called expanded octets. But for second period, carbon, nitrogen, oxygen, fluorine, that's a law. And laws, no. And so this is the octet law that you just violated. You can't violate the octet law because this is 2, 4, 6, 8, 9. 9 electrons is not possible. So let's rethink it then. It's not going, the electrons, well, unless there's another place. Is there another place we can fit electrons on hydronium?
Unless we could somehow break hydronium into water.
Well, they did. It broke into water.
So can we put those electrons on water? Or
I suppose. But where on water would you put extra electrons?
I'll put it inside the oxygen.
Inside the oxygen?
Yeah. I feel like that would be the wrong answer. So I wouldn't want to put it in
I think
water
that's
either.
inside the electron we have what are called the core electrons, and for the first shell there's only 2. And so maybe we could put 3 in the first shell, the 1s shell. No, it's going to happen. So we got to figure out where those 5 electrons went. Chlorine? Chlorate? Yeah. Okay. If the 5 electrons go to chlorate, then what would form? Well, the 5 electrons, we already have these oxygens here. Chlorate already has an octet. And so if we look at chlorate, its Lewis structure, chlorate is 1, 2, 3, 4, 5. Chlorate's Lewis structure would look something like this, where each of these oxygens has a negative formal charge. 1, 2, 3, 4, 5, 6, 7. It's supposed to have 6. And this chlorine's going to have 1, 2, 3, 4, 5. Chlorine's supposed to have 7, so this is going to get a +2. The formal charges are quite high in chlorate here. But when we add them up, okay, +2 minus 1 minus 1 is 0 minus 1. So this whole thing carries a net -1 charge. It's chlorate. And so where can the electrons go here? Well, that's the formal charge, but when we look at the oxidation state, it seems to be okay here. If we look at the oxidation state on chlorine is, okay, when we count oxidation states, winner takes all, right? And so oxygen versus chlorine, who wins? Okay, so none. So chlorine ends up with 2 electrons. It's supposed to have 7. It ends up with 2 electrons. That means its oxidation state is +5. And oxygen's oxidation state is -2. We never compare apples and oranges. We just compare apples with apples and oranges with oranges. So, formal charge gives us a picture of what's going on here. And this is very useful for Lewis acid-base reactions. But oxidation state is going to be very useful for redox because chlorine really is 5 electrons short. And so that seems to work out, right? Because we have 5 electrons being lost. And this one's 5 electrons short. And chlorine likes to actually have not 0 charge. Chlorine likes to have, what, -1 charge. Like this. This is pretty stable, chloride. When we look at the redox chart, chloride doesn't want to lose that electron. And so what has to happen is for chlorine to gain some electrons, we have to kick off the oxygens. In order to kick off the oxygens, we need what?
We would need a good acid.
Yeah, normally when we're looking at redox and we want to kick off oxygens, we need acid, which is hydrogen ions, H+. This is a different way of writing it. This is not the normal way I write it. Some people love it because it's more accurate. Hydrogen ions, are they very stable in water? Hydrogen ions.
Just the ions. They shouldn't be that. They have no electrons.
This is the way I would have written it. I would have just copied the half reactions or made the half reaction for chlorate to chlorine. Ideally, chlorate would have loved to go from chlorate to chloride because we know chloride is quite stable. Versus chlorine's not so happy. Chlorine still wants to take another electron. But that's what happened. When you mix these up, it depends on the conditions. Did it go all the way? We call this reduction. Was it reduced all the way to chloride? No, it was only reduced to chlorine. And so we need the 6 H pluses because we have how many oxygens? 3 oxygens, and we need to form 3 H2Os. Do you guys recall this pattern? I think,
H plus being unnecessary.
yeah, could be potentially. All right, so let's go ahead and finish the oxidation states here. When you look at the oxidation state that you got for this one, oxygen, -2. Okay, hydrogen or oxygen first, and then oxygen. Did anything happen to hydrogen and oxygen? No, so hydrogen and oxygen is not a participant in this. See, in order for redox to occur, we either have to lose or we have to gain electrons.
I have another guess.
Okay, go ahead with your next. We'll go option C.
So ClO3 minus would be the reducing agent,
Okay,
and then Cl minus is the oxidizing agent.
okay,
And then chlorine would be Ra and OA.
okay. Anybody else? For option D?
No.
Stretching.
Yeah. I don't know.
All the vocabulary of redox gets confusing, and it takes some time for it to click. And so we have oil rig. Oil stands for what? Oxidation is loss of electrons. And then rig is, production is gain. And so who's undergoing oxidation here?
Chloride.
Chloride is undergoing oxidation because it's losing electrons. So oxidation is loss. We're losing electrons. Chloride's undergoing oxidation. So is chloride oxidizing itself, or is somebody else oxidizing chloride? Yes, something else is oxidizing chloride. And what do we call that something else that's oxidizing chloride? Do we call it a reducing agent? Or do we call it an oxidizing agent? What do you guys think? Well, I hear mixed, so let's settle it. Oxidizing agent? Alex, you call it a reducing agent?
Yeah.
Now, the agents cause the oxidation or the reduction. So we call it an oxidizer. It's kind of weird. Oxidizer, oxidizing agent. So tell me a good oxidizing agent. Oxygen is a good oxidizing agent. So if oxygen is a good oxidizing agent, what does it do? Does it lose electrons? It gains electrons. And so oxidizers, oxidizing agents gain electrons. And they cause oxidation. And so each oxygen atom wants to gain 2 electrons to form the oxide, or the octet. O2 already has an octet, but O2, it has to share. If you recall, O2 looks like this, and that means oxygen has to share with another oxygen. This is perfectly covalent, and so they have to split these 50-50. But oxygen doesn't like to share. Oxygen wants all the electrons. So even against chlorine, it wants to take all of them, not share them. So this is why oxygen is a good oxidizer, because it wants to take the electrons for itself. And that means if oxygen takes electrons, then it undergoes reduction. And so oxygen undergoes reduction, but we don't call it the reducing agent, we call it the oxidizing agent. So always remember, it's flipped. The agents are flipped. So it's like, okay, let's say you were robbed of your lunch money. If you're robbed of your lunch money, did you rob yourself or did somebody else rob you?
I think someone else.
Yeah, that's the same kind of thing. You know, if I was robbed, then I'm the robbing agent. But you're not the robbing agent. Somebody else was the robbing agent. Okay, let's see. So do we have an option D? Anybody? Okay. Okay, ClO3 minus would be the OA because it is robbing chloride of electrons. Yeah. And therefore chloride would be robbed or oxidized in the process. So it's causing chloride to become oxidized and it's gaining the electrons here. And so chloride would be the reducing agent. And then this is weird, but this is actually correct. Some of the chlorines, one of the chlorines gained 5 electrons. 5 of the other chlorines lost 1 electron each. It's kind of weird. And so altogether we have 6 chlorines here. And so going backwards, this is the way it would be. Going backwards, 5 of the chlorines would take. And so this would be 5 of the chlorines. And then 1 of the chlorines would lose. And so 5 of the chlorines would take 1 electron each, and 1 of the chlorines would lose a total of 5 electrons. That's not so favorable. And so there is a driving force to this this particular reaction here in the forward direction. Forward direction is downhill. Going backwards is uphill because of this. This is called a disproportionation reaction. The reverse reaction here is disproportionation because some of the atoms of that gain of the chlorine and some of them lose. There are other examples of disproportionation as well. And that is the same species is both the oxidizer and the reducer. And this can happen as a, as a product going backwards, or it can happen as a reactant going forward. So we could have disproportionation in both directions. Mercury is a classic example of this. It turns out that mercury 2 salts aren't so stable. And so mercury 2 salts tend to disproportionate into mercury 1 salts and mercury metal. And so we see disproportionation there. So where some of the mercuries gain, some of the mercuries lose. All right, so the method, we'll just shorten the method. If you want to do this quickly, the first thing you have to do is write the oxidation states. And then you have to determine who gains, who loses. So to go from +5 to 0, that means this had to gain +5 electrons. And we only have 1 of them, so it's 1 times +5 electrons. And so this is +5 electrons, this is reduction. And the oxidizing agent undergoes reduction. And over here, this is oxidation. And so it didn't oxidize itself. The oxidizing agent oxidized it, and therefore this is the reducing agent. The other way of thinking about this is oxidizing agents, are they electron rich or electron poor? Oxidizing agents are electron poor, and reducing agents are electron rich. So which one is richer, chloride or chlorine and chlorate? Chloride is a lot richer, isn't that?
Yes.
I mean, but we wouldn't call it rich, we'd just call it happy as is. And so it makes sense that out of these two, it's going to be the reducing agent. And then chlorine and chlorate, that's poor, so this will be the oxidizing agent. That's another way of checking if you have it down. But it takes some time to vocabulary now. Calcium carbonate plus sulfur trioxide yields calcium sulfate plus CO2. This, okay, if you want to figure out what the oxidizer and reducers are, the first thing you need to do is to write the oxidation state. So let's go ahead and do that. Calcium carbon or oxygen, which one goes first? Well, calcium only has one charge.
Yeah,
So, yeah, and that would be plus 2.
Oh, two, sorry.
Yeah. Okay, then carbon versus oxygen, who goes? Oxygen is more electronegative. It's going to go at -2. It's going to get its favorite charge. And that means carbon will be +4. Sulfur versus oxygen. Oxygen is more electronegative at -2. And that means sulfur is +6. Yeah, sulfur is not the happiest here at +6, but it's not terrible because how do you know? This is the two-pronged approach. You know, you think +6, wow, that's a really high positive charge, right? But then you start thinking, what else is +6? What else is +6 is sulfate. And when we look at sulfate, oxygen is -2, and then sulfur is +6 here in sulfate. And sulfate salts, are they stable? Yeah, there's lots of sulfate salts that are stable, so it's not as bad as you might think. Otherwise, sulfate salts would be very reactive, like perchlorate salts or chlorate salts or something like that.
So I think that sulfur can tolerate with plastic.
Yeah, right. And that's not based on theory. That's just based on experimental observations. You know, your experimental observations of knowing sulfate salts are kind of stable. So, a lot of the 8 salts are stable because we live in an oxidizing environment. The air in this room is 21% oxygen, and so that makes these oxidized species stable versus the unoxidized. Compared to sulfur, do you think sulfur, elemental sulfur, is very stable? No, it burns easily. Sulfur, very easy to burn into like sulfur dioxide, sulfur trioxide. Okay, and then let's go on. Calcium sulfate. Calcium goes first at
+2.
then what? And then
Sulfur +6.
it's sulfur at +6. So then we go to CO2.
Oh, oxygen goes first at -2. And then carbon at +4.
Okay, so what happened here?
Nothing. No oxidation.
This is not redox. Okay, if it's not redox, then is this metathesis? Does this look like a double replacement reaction to you? No, this is not metathesis. Is this a Bronsted acid-base reaction? No, this is not a Bronsted. What must it be? This must be a Lewis acid-base reaction. And so I was thinking we're going to have like, I think a combination, you could have many different kinds of combination reactions. So just focusing on redox for right now, element plus element, combination, compound decomposition, redox, combustion, single replacement, what else?
Or if Combustion, was it combustion? Wait, does that say combustion or combination?
Combustion.
Sorry, that's my fault.
No, I just sloppy.
Combustion, single replacement, double replacement.
Double replacement is not redox.
Oh, this
Double replacement is metathesis.
Oh, this is up.
Double replacement, none of the oxidation states change in double replacement. Yeah. And also acid base, none of the oxidation states change in acid base.
Skeleton.
In redox, we have to have change. Okay, before skeleton, I talked about what?
Chart method.
Chart method. These are things if you do daily review. Like I like to do, one thing I like to do is like, when I was a student, I didn't like back-to-back classes. The reason I didn't like back-to-back classes is because immediately after class, what I do is I read through my notes, and then the stuff I couldn't write down because I'm a slow writer, the stuff I couldn't write down, I'd fill in the blanks because I would remember it. And so I try to fill in the blanks. But sometimes I forget, what's going on here? And so normally what I would try to do is I try to get it cleared up that day or the next day immediately. So because they say your memory, after one day, your memory drops. You forget a lot of stuff. So, What's that? No. I would, okay, this is the way I worked it out. Let's say I had a class, 50-minute lecture. And then right after class, I'd read through my notes. This is when I was a student at UCLA, I had a routine. After class, I would go to, there's a coffee shop, Kirchhoff Coffee Shop. I'd sit down and grab a coffee and then read through my notes and then fill in all the blanks that I could remember because I wasn't quick enough to write, but fortunately I remembered it once I read it, because when you read it, then it triggers certain memories. But there's still holes in the notes. And so the holes in the notes, I'd make sure I got all the holes filled before the test day. And usually I try to get them filled the next day. Actually, classes are like Monday, Wednesday, Friday there. So the next time we met, I try to get it cleared up. But I tried to make it a point to read the notes that I just took right after class. And I found that to be very effective, versus waiting until right before the exam to review my notes. That I found very ineffective because that's the way I used to do it. Right before the exam, I'd start to review for the test. And then, there'd be so many holes and so many things I didn't understand in the notes that it was just overwhelming. And so, then you resort to other things like the night before the test, you resort to, pounding your head against the wall so that it might jar some memories free, that kind of thing. And so I used to do that a lot. It used to be a stress. It used to be highly stressed. But if you do this, then that way, like, if you read it every day, then it's simple, what are all the redox methods? Element combination, decomposition, combustion, single replacement, chart method would be one, and skeleton, right? And then you work on these. Okay, this is an example of a skeleton. This is an example of a chart. This is an example of single replacement. And then once you have those down, because you've seen those, then you can start working on hybrid ones. Hybrid ones are a little bit of twist of both, right? And so hybrid ones would be an example like this. Because we have the basics down, now we can really start mixing and matching and doing other stuff. And so let's take some sugar, table sugar, which is called sucrose, C6H, not C6, that would be glucose, C12H22O11. This is solid sugar, which is given the name sucrose here, table sugar. Plus, let's do this. I'm going to do sucrose plus potassium dichromate. Potassium dichromate, what's the formula for potassium dichromate?
KCr2O7.
CR2O7, close, very close. K2 CR2O7. Yeah. Aqueous. This will be aqueous. And we're going to throw in some acid in here. Let's throw in some hydrochloric acid. Hydrochloric acid's formula is HCl. One of those ones that will be on the quiz later on. If you get hydrochloric acid wrong, then
So you're about to expose me.
don't major in chemistry. You can major in something else, but you'll be under constant grief for getting that. I mean, I've seen it wrong lots of times. You know, people. All right, so what would you think? Well, you would think, wow, this is going to be double replacement, right? If this is double replacement, we would think maybe we're going to form some. This is dichromic, so we'd form dichromic acid, right? This is dichromate. Eights get turned to ic acid, so we form dichromic acid. And so this is one potential reaction. We'd have potassium dichromate plus HCl, two of them, to make H2Cr2O7, dichromic acid. And what else? Potassium chloride. So here we're going to go from stronger acid to weaker acid. But do you think that's a very big reaction there? No, because when we think about the chemical properties, tell me what do you know about dichromate? What do you know about potassium? Potassium ions, tell me some chemical properties of potassium ions. They're water soluble. Yeah, this is why we can break it up into ions here easily. Even if it's in the solid state, it's okay. It's still ions, but they're going to react a lot slower. And so potassium ions, tell me some chemical properties of potassium ions. Let's go. Do you guys remember how to do chemical properties? All right, tell me what kinds of there are billions of chemical reactions, aren't there? Or maybe more, trillions of chemical reactions. Should we go through all of them?
Yes.
No. Yeah, okay. Does potassium ion react with water?
Yeah.
Does it react with air? Does it react with space? What does it react with? Dirt? Yeah, probably some dirt. No, we don't want to do it that way. What do you want to do? Metathesis. Okay, what metathesis reactions does potassium undergo? What precipitates does potassium ion form? None. What gases does potassium ion form? None. What weaker acids does potassium ion form? None. So metathesis, no reactions. It's unreactive. So metathesis, it's pretty stable. Potassium ions are pretty unreactive. What else do we look for? Redox. Okay, for potassium, will that lose electrons or will that gain electrons? It will gain electrons. So potassium ions are an oxidizer or reducer? It's going to take some time for it to click. That time is not like overnight, right before the test. It doesn't happen. You got to kind of review it every day, and then pretty soon it just clicks. Yes, it's an oxidizer. Then you got to think, is it a good oxidizer or poor oxidizer or moderate? It's a really bad oxidizer. Because people eat this stuff in sea salt. Do they worry about oxidizing? No. Are they going to take antioxidants to prevent the damage caused by potassium ions? No. In fact, they probably want it because of electrolytes. And so for redox, it's really, really bad. In fact, it's the second worst oxidizer on the chart, isn't it? It's like number 2 worst oxidizer. How do you know? Because once in a while you read through the chart and you see, and then you might remember, if you might remember these kinds of things. Okay, so if it's not metathesis and there's no redox, then we look at, and is potassium ion a good proton donor? Are there protons to donate? Yeah, in the nucleus, but is it really going to donate a proton from its nucleus? No, so this is, as far as Bronsted goes, we eliminate. Now, Lewis, of course it could be a Lewis. Lewis are a bit more tricky. Lewis, we use something else. When we predict Lewis acid-base reactions, we use something called HSAB. This is for Lewis. HSAB is called, stands for hard, soft, acid, base theory. It's kind of interesting. The guy who developed HSAB is a professor at UCSB. I took a class from. But this is typically what's used, hard, soft, acid-base theory. We're not really going to do it, really. So, for example, a hard ion, let's say, would be iron. Iron 3 plus is hard, whereas potassium would be soft. Do you see the difference?
Yeah.
Which one's going to be much more reactive? Iron 3. So iron 3 is going to behave a lot differently than potassium ions. You might have seen iron 3 before in our Bronsted chart, and that's because it's quite a bit more reactive. But we're not really going to get into this that much. Oxide is considered hard. Actually, oxide's even small. I didn't do this correctly. This is just relative size. Versus sulfide is considered soft. Do you see the difference? And so what hard, soft, acid-base theory is hard likes hard, and so hard likes to react with hard, and soft likes to react with soft. This is why, like heavy metals are typically soft, and they like things like sulfur, which are also soft. And so this stuff is just, you don't have to know this at all. And so soft is good, and hard is good. But hard soft is not as good of a combination. And then we go through it. This is based on quantum mechanics. So even in terms of Lewis, potassium ions are unreactive. So in terms of Bronsted, absolutely nothing. In terms of Lewis, they're not much. Nothing, pretty much. And so potassium ions are very unreactive. They're stable. They're like sodium ions. People eat this stuff and not worry about it. Would you eat dichromate? No. You probably shouldn't eat dichromate. What do you know about dichromate? When I look at dichromate, automatically I think powerful what? Automatically I think powerful oxidizer. This is a powerful oxidizer.
Do you know what oxidizers do to us, like the acid
They cause oxidative stress. No, there are different things. Actually, there's some good YouTube videos out about this. That's one of the things they're talking about COVID. When you get COVID, it ends up producing a lot of oxidative stress, which ends up causing things like blood clots and other stuff. There's actually, there's a great series of YouTube videos done from this professor at UC Riverside Medical School. This professor is like board certified in like 4 or 5 medical specialties. and he did a whole series of oxidative stress videos. Oxidative stress, your body, when you undergo a metabolism, naturally you have oxidizers. Some of the oxidizers are like superoxide. You've heard of superoxide? Do you guys recall does anybody know the formula for superoxide? You think that superoxide, that's obscure, that's not very common, that's not on the list. But I would have had it memorized. You know how I would have had it memorized? I would have had it memorized because it was in my notes. And if I read my notes, even though it's obscure and not that common, I still would have remembered what superoxide is because I went through my notes every single day. And if you do something every day, then you can't help but memorize things.
Is it O2 minus?
O2 minus is the superoxide. And so normally when you undergo metabolism or when you do certain things, like sugar, and in fact, we're coming to this. Sugar, actually, before we get to sugar, let's talk about this, and then I'll come back to the oxidizers here. HCl, tell me well, we already talked about the chemical properties of this. Could you list them? If I put that on a test, could you list them for me? Because we talked about this how many days ago? Like many, many days ago, right? Or would you have to memorize this right before the test, or would you just not have time to even think about it? You guys remember we went through HCl, the chemical properties? Can you tell them to me? This should be easy points, right? I would think that would be easy points. What are the chemical properties of HCl? Easy points. I would have thought it, but maybe do you think that would be easy points or not? Yeah, and so that's it. I had to shift because I was used to studying a certain way. When I went to UCLA, at orientation, they say, your GPA is going to take a dump. Basically, it's going to drop, right? And I thought, no way, not my GPA. I'm going to keep it up. And so what I did was I just focus, and every available minute I studied. Every available minute I studied, and still my GPA took a dump. I mean, I was worried. I wasn't even going to pass. I was worried I wasn't even going to pass Chem. The first exam I got, I pretty much failed the first exam. And there's the midterm exam and then the final. I think I got like a D or something on the first exam. So I thought, wow, I'm in trouble here.
For HCl, one of the chemical properties is metabolism, and that it would be stronger than water ions.
Water does not form ions, unfortunately.
No.
Yeah, water is
stronger than water.
But the metabolism is ion combinations, and water is molecule, right?
For H plus.
There's going to be some H plus, but is there going to be enough H plus and OH minus to really do anything in terms of metabolism? No. I mean, did this conduct any electricity? No. There's so few ions, we didn't even see any kind of light in there. And therefore, since there are some ions there because of pH, I talked about pH. But therefore, water we consider, even though it does ionize, it ionizes to such a small extent, we essentially call it non-electrolyte. But non-electrolyte, we should put a little asterisk here because it's technically not 100% true. We do this for a lot of things, that we ignore some of the minor species completely for this. And so, what metathesis is ion combination. And so these are types, all this stuff is not easy because it's just like oxidizing agent, reducing agent, all that stuff is all mixed up, and it's all mixed up. So what you have to do is you have to go through it, day by day and then try to sort it out in your mind and then have it click. and eventually it'll click. And the same thing with these reactions, you know, and the same thing with these properties. What you do is you can just kind of memorize it, at least initially, and then pretty soon it clicks, and then you can figure it out, you know, reverse engineer it. So we went through it. They're metathesis properties. What were the metathesis properties? You know, this would have been easy points for me because H plus reacts with all anions, basic anions, stronger than, not water, anions. Anions, we need an anion.
Like chloride?
No. All right. Well, you got to think about it, and then you got to sort it out. But the thing is, can you imagine, like, right before the test, you know? And so going back to the story, I thought I was studying great. You know, I was spending every minute, but I wasn't studying the way I needed to study. And that's when I shifted. You know, I shifted to where I made sure that I understood everything in lecture before the test. You know, sometimes you can. There at UCLA, like organic chemistry, they have lecture notes that you can purchase. You know, my notes weren't nearly as good as professional notes, and so I always bought the professional notes. They're kind of expensive, but they're so worth it. And then I'd review those, and then I'd do that every day. So then I had everything in the lecture notes memorized. So if anything popped up that was anything similar to any kind of lecture problem, I thought easy points. And then I could concentrate on the harder stuff, like this, you know, or at least have time to think about the harder stuff. And so you might want to consider doing that. I started reading. At that point, I started reading, you know, how to study or books on studying, books on memory, this kind of stuff. Because I thought, you know, something wasn't, you know, quite clicking. Something wasn't quite working out. But going back to this, you know, it's not just memorizing, you know, but if you have a lot of basic stuff, basic tools memorized, then you can do a lot of things, you know, with those. It's like if you learn how to use tools, then you can build a lot of things from those basic tools. And so that's doing the other stuff, the harder problems. But going back to this, we know this is a powerful oxidizer, but this powerful oxidizer needs what? We need a reducer, and for dichromate to be a powerful oxidizer, because we also need, because of the oxygen, we also need H plus. But we have H plus here, and so here we have a powerful oxidizer, which is the dichromate and the H plus combination. And so we're going to oxidize something. Maybe we're going to oxidize, what's this? Chloride. Maybe we're going to oxidize chloride. Is chloride easy to oxidize? No. It's not. This is not easy to oxidize. But it's possible we could oxidize it. Because would you consider chloride very electron rich? No. We wouldn't. What about sugar? Is it possible to oxidize sugar? In other words, is it possible to burn sugar? Some people like to gently oxidize sugar. They gently oxidize sugar to make caramel, you know, like caramelized sugar. But if they are a little bit too aggressive, they're going to make, not an explosion, they could make an explosion. They're going to make charcoal. Charcoalized sugar doesn't taste very good. It tastes like coal. Or they might just burn it. If they completely burn it off, you know, that's what some people do. You know, some people get these black carbon deposits on their cookware. You know what they do? They try to burn it off. Eventually it'll burn off because they're going to burn it off to what? CO2. Now your body does this too. We can use the oxygen to burn it, but you know, when you eat sugar, you know what your body does? Your body oxidizes it. And so when you eat sugar, your body is going to oxidize it. Your body's going to inhale oxygen, but it doesn't happen in one step. You know, did I tell you about the flame? You know, when we have methane in the flame, this looks like it happens in one step, right? But it doesn't happen in one step because what is the blue color from? Yeah, atomic oxygen. Where's the atomic oxygen in this equation? It's not here. Do you know it wasn't until this is such a simple reaction, or it looks like such a simple reaction, this reaction really wasn't well understood until recently. I think it was about 20 years ago or 30 years ago, somebody finally figured out all the potential steps that occur in going from methane and O2 to CO2 and water. And they had, I think, about over 1,000 possible branches here. Some of them, you know, and so there are a whole bunch of little steps here to get to this. And this is what we call the overall reaction here. In your body, when you eat sugar, do you automatically spit out CO2? No. You know, when you burn sugar, you get energy. Water and energy. And so whether you burn this in the flame or you burn this in your body, this is going to take a lot of steps. The steps in the flame are totally different than the steps in the body. When you go in the steps in the body, you create other species. Just like in the flame. You know, is there atomic oxygen here? Do you think atomic oxygen is very happy and stable? No. And so sometimes when you do this, you create, you know, things. You create things like free radicals and superoxide and other stuff. And people take this supplement, superoxide dismutase. Have you heard of that one? You can buy it like at Costco or wherever, some pharmacy or supplement store. Yeah, superoxide dismutase. You can look, you know, people are worried about superoxide and oxidative stress and damage. But those types of things happen. So if you're interested in that in the biological end of things, watch this guy. It's called MedCram. Yeah, he does a lot of paid things on here. Like if you're a medical student or if you're a doctor and you want to brush up on things. But there's a lot of free stuff on there. And it's pretty interesting. But he has a whole series about oxidative stress, and he came up with a hypothesis on COVID. His hypothesis was causing the blood clot and blood issues, and he had the mechanism for that. So it's pretty interesting to see. So you can check that out.
When this is kind of a small story, but when I was in middle school doing aerospace, one of our preferred reactions was taking sugar and tree stump remover and using it as a rocket fuel.
Oh yeah.
Yeah, it burns very quickly with a lot of power.
Yeah, sugar is a great fuel. It fuels rockets. It fuels your body. And fuels are the electron rich or electron poor? Electron rich. And so when I think of sucrose, I think electron rich. But when I look at the oxidation states, it doesn't look like it. Because oxygen's -2, hydrogen's, oh, actually we do hydrogen first. +1, then oxygen -2. That means carbon is 0. But this carbon's not like coal. You know, charcoal or coal or diamond has carbon in 0. But because of the structure, because of the bonds, this one's a lot easier to break than diamond. You know, diamond has carbon in 0. And so we don't normally think, like if you ran out of sucrose, could you start eating diamonds? Even though they both have, potentially you could, but it's too hard to break the bonds in diamond. That's why you can't. But potentially diamonds could act as a fuel, you know. You probably don't want to try that, but this. Okay, so as far as chloride, water, sugar, which one's the easiest to burn? Chloride, water, or sugar? Sugar. And so what I think of when I look at sugar, this is a good blank agent. This is a good reducing agent. And so I would think this is a great reducing agent, and I think this is a heck of a lot easier to burn than chloride. I tried to burn chloride, sodium chloride before. It doesn't burn, at least in the flame. It didn't appear to burn to make chlorine gas. And I've tried to burn water before, but it's very hard to burn water, right? Very hard. And so so what do you think the potential reaction here is? It's going to be between. So what we do is, this is the hybrid chart method. The strongest oxidizer is going to be dichromate with acid, and the strongest reducer will be sucrose. Okay, so this is what you do. If you have the basics down, you might be able to do this problem. And this is why I call it kind of the hybrid method. Well, dichromate and H plus is easy because that's on the chart. And so dichromate is going to require how many H pluses? 14 H pluses. And do you know what chromium, the oxidation state of chromium is here? Plus 6. This is called chromium 6. And it's going to be plus 6 electrons. It's going to go to chromium, 2 chromium 3s, chromium 3 plus ions. And how many waters?
14.
Well, actually, we need 14 hydrogens, which is going to give us 7 waters. So we have 2 of these. Chromium 6 is going to 2 of these chromium 3s, and so we need to gain a total of 6 electrons. So this is times 2, which will give us plus 12. This is times 2, which will give us plus 6. We have plus 6 electrons. And that's why we have the plus 6 electrons here. All right, so this one's easy because we can copy this off the chart. Is sucrose on our redox chart? Okay, there's 2 reasons it might not be on the redox chart. One, it doesn't have very good redox properties. That could be why it's not on the chart. Or 2, there's just not enough room to include everything. What do you think? Sucrose doesn't have good redox properties, or there's just not enough room to include everything? Not enough room, yeah. Because it does have good redox properties. It's a great reducing agent. It's a great fuel. It's a really good fuel. And so what do I do? Okay, skeleton redox I could do. But in skeleton redox, you're always given the product. But in this case, we aren't given the product. So how can we balance it? Unfortunately, we can't put a question mark because, I'll tell you the reason why. We have 12 carbons here, and we have 0 carbons here. So how should we balance that? What should we add?
12 CO2.
CO2, yeah. Well, actually, we have choices because when we burn sugar, we could burn it to different levels. That is, we could partially burn it or we can completely burn it. In this case, you're thinking we're going to completely burn it. And that makes sense because we don't know. It could be that we just add carbon, and that carbon would be the carbon deposits that you'd see, like the charcoal. And it could perfectly happen that way. Or it could have burned to carbon monoxide. It all depends on the conditions. But since we don't know what the conditions are, we're just going to assume that it goes all the way to CO2 because that's what's going to happen in your body. When your body eats this stuff, it's going to try to maximize the amount of energy it gets by completely oxidizing it to CO2. So that one step there, you did, Tristan, is A lot of people wouldn't figure that out. A lot of people would be stuck there. They wouldn't make any assumption. And so here, if you put carbon like soot or charcoal or whatever, it could be perfectly fine, or carbon monoxide. But since we aren't told, we'll probably just take it all the way to CO2. And so all of a sudden, that makes this problem much, much more difficult. So do you know how many people can actually do this problem on a test? Very few, If I gave this problem on a test, it would be like a couple of people. That's it. Sometimes only one. All right, now we can use the chart method. So the tricky thing was we had to assume complete oxidation. So we assume complete reaction to CO2. And now we can balance it. So we have 12 carbons, 1 carbon, and then we'll just put 12 out in front here. And then 11 oxygens, 24 oxygens. And so 11 oxygens, we're going to need 13 H2Os here. And then 22 plus 26, we have 48 hydrogens and 0 hydrogens. So we'll need 48 H pluses over here. And then the charge. Charge is going to be 0 here and plus 48 here. And so how many electrons do I get? 48. So this is electron rich. 1 mole of sucrose yields 48 moles of electrons. That's electron rich. And so we'll have, if I did it correctly, I'll double check. C12H22O11 plus 13 water yields 12 CO2s plus 48 H plus 48 electrons. So I have 12 carbons, 22 plus 26 is 48 hydrogens. 11 plus 13 is 24 oxygens. So there's 24 oxygens. And then the charge is neutral on the left, plus 48 minus 48 is neutral on the right. So this would be my balanced half reaction here for this. And then I'm going to combine it with this here. So this one needs 6 electrons. This is 48 electrons. So times 8, yeah. We'll just take the first one and multiply by 8. It's 8 times that. But before I leave the half reactions, let's do this so we can see what the driving force is. Because we don't know what the driving force, if there is even a driving force, because we didn't detect the products. We're just trying to predict the products of this. And so over here, dichromate and H+, as we said before, this is our oxidizer, and therefore this must be our conjugate reducer. Chromium-3 in water, sorry, reducer. And then sucrose and water will be our reducer over here. And that means CO2 and H+ will be our conjugate oxidizer here. Okay, now let's go ahead and combine these. It's easiest to do the assignments in the half reactions. Let me tell you what this is called. Is this the reduction half reaction or the oxidation half reaction?
Reduction half reaction.
Yeah. Even though it's the oxidizing agent?
Reduction.
Yeah, okay. So this is, you're correct, this is the reduction half reaction. So if you look at our chart is a chart of reduction half reactions, or chart of reduction potentials, they call it. And so this is the reduction half reaction. But where's our chart of oxidation half reactions? Well, we don't need a chart of oxidation half reactions. What we do is we take all the reduction half reactions and reverse them. And so this would be an oxidation half reaction. and our reducing agent undergoes oxidation here. And so just combining everything, we'll have 8 dichromates plus 8 times 14, so 80, 96. 96 H plus 48 electrons plus C12, sorry, C12 H22 O11 sucrose plus 13 H2O. This is going to produce 8 times 2, 16 chromium 3s plus 8 times 7, 56, thank you.
And the H pluses are
112? Oh, did I screw that up?
Yeah.
On top? Okay, thanks. 112. 56 waters plus 12 CO2s plus 48 H plus 48 electrons. So the 48 electrons should cancel. What else cancels? 48 H pluses will cancel. So 112 minus 48 is 60, 70, what? 74? 64 H plus. H2Os cancel. 13. I think I could do this one. This would be 40. Is that it? 43. Maybe I can't do that one. But fortunately, I'll double check it at the end to make sure I didn't screw it up. And that's what we do. If it doesn't work out, then I'll just go back and try to figure out where I made my mistake. Anything else cancel? No. And so I'm going to have 8 dichromates plus 64 H plus 1 sucrose yields 16 Cr3 plus, chromium 3 ions, plus 43 water plus 12 CO2. Okay, CO2 is a gas, water is a liquid, everything else should be aqueous. Although this was solid, sucrose is soluble, so it'll dissolve in water. It's a non-electrolyte, so it doesn't break up. All right, let's look for a driving force. So dichromate and H+, this is our oxidizer. This is our reducer. Going backwards, chromium 3 and water will be our reducer, and CO2 will be our oxidizer. Now, the problem is this. Dichromate and acid is on our chart. Is CO2 on our redox chart? CO2 is not on our redox chart, but, we have a two-pronged approach. Our two-pronged approach is, theory or, what's on the chart versus experience, observations. And so this one, you should tell me, what do you think is going to be a more powerful oxidizer? Dichromate in acid or CO2? Yeah, this one, there should be no question. That's going to be stronger, this is going to be weaker, and we expect driving force. That means this, which is easier to burn? Sugar or chromium 3 ions? Sugar. Chromium 3 to convert it to chromium 6 is hard. The oxygen is going to come from the water too. And so we don't have to have any oxygen here because there's no O2. And so the oxygen is coming from here, which is going to release H+. And so this is weaker. And so we have driving force. So we got to watch out, dichromate and sugar. It can burn the sugar, and dichromate is better at burning sugar than oxygen because dichromate is a more powerful oxidizer than oxygen. So when you said about sugar, you know, there have been lots of sugar explosions, as a matter of fact. Like, not just sugar, like powdered sugar. There's a powdered sugar explosion. I showed this video from OSHA, I think it is, or department. And they have all these animations. So they had all these sugar conveyor belts, you know, with the powdered sugar. And the problem is the sugar dust went everywhere. And so the finely divided sugar dust went into the room, and then there was a spark. And then they had a big explosion. And I think 2 people were killed in that. But it's actually quite common, these sugar explosions. Well, dichromate's even more powerful, but it's not a gas. And if it's solid sugar, it burns a lot slower. But if it's solid sugar dispersed in a fine aerosol, then it can explode. In fact, any good fuel, like powdered metals, you know, powdered metals on the bottom, on the bottle say flammable, potentially explosive. Because you can do that rather than having powdered sugar filling up the air in the room, you could have powdered metal, you know, finely divided powdered metal, although it'll settle a lot faster. But powdered metal dispersed in the room and then have an explosion as well. You know, the explosion is just rapid reaction. Are there any questions on this? Do you think you could do something like this? No, maybe not. But what you do is you just copy it, right? That's the first step. It's not like you have to come up with it. You just copy it, and then go through it, and then go through it, and then eventually it just clicks. And then that's a step. If you don't understand it, it's not a big deal. I didn't understand most of the stuff that was given in the PCAM class. I didn't understand anything. In the lecture, I sat there and thought, wow, what the heck is he talking about? And then I would go home and try to sort through and figure it out because I had no clue that's why I did so poorly on that first exam. I had no clue what he was saying. I didn't understand the lecture at all. And so that's what I ended up doing, tried to figure it out. Fortunately, I was in a nosedive, but fortunately I was able to pull out of the nosedive and get it right on the final exam. But I thought, you know, for sure that class was going to. Anyway, all right. Why don't you guys work on this worksheet here? Okay. And then if you have questions on the worksheet, we'll just go ahead and ask. And then at the end, we'll have our nomenclature quiz.